Section 3.3, Dividing Polynomials. So a lot of this will be hopefully review material from a Math 1010 course where you discussed dividing polynomials using long division and synthetic division. We will extend that discussion into how it relates to the factors and the zeros of polynomials. So just a little background on factoring to begin with. We talk a lot about factoring quadratic expressions. So x squared minus x minus 12, for example, factors into x minus 4 times x plus 3, the two factors here. Factors are parts of a product. Product means multiply, a product of the original expression. So a factor always multiplies with something else. To form a factor, it has to be a product, something multiplied by something. And it's something that you've done since elementary school. For example, 6 has factors of 2 and 3. 2 times 3, 2 is a factor of 6, and 3 is a factor of 6. And the question is, and I know it's a simple question, or what seems like a simple question with numbers, but it's actually an important concept to understand when we're talking about dividing polynomials and what factors are of polynomials. So why is it that 2 is a factor of 6? Or how can we show, or how can we prove that 2 is a factor of 6? Well, it's because 2 divides into 6 evenly with no remainder. 6 divided by 2 is 3 with a remainder of 0. That's why 2 is a factor of 6, and that's an important concept and something I'm going to touch on multiple times in this section and in section 3.4 and in section 3.5, the fact that when you divide, there is no remainder. So again, just to reiterate, to prove that an expression is a factor of another expression, you need to be able to divide and have no remainder. And another way of writing this, if 6 divided by 2 is equal to 3, then you can also write that 2 times 3 is equal to 6, because this statement here proves that 2 is a factor, but it also gives another factor, because remember what I said, the factors always come in pairs. So if 2 is a factor, then it has to multiply with something else in order to equal 6, and it's 2 times 3. So is 4 a factor of 94? How could we show that it is or that it is not a factor of 94? And the answer is, well, we divide and see if there's a remainder. So if we quickly review the long division algorithm here, 4 goes into 9 2 times 8, or 2 times 4 is 8, 9 minus 8 is 1. Then you drop down the 4, 4 goes into 14 3 times, 3 times 4 is 12, 14 minus 12 is 2. Nothing more to drop down, so 2 is the remainder. So it has a remainder. Therefore, 4 is not a factor of 94. 94 divided by 4 is 23 with a remainder of 2. Another way we could write this is 94 is not equal to 4 times 23. It's equal to 4 times 23 plus the remainder of 2. So 4 is not a factor of 94, neither is 23, because it had this remainder. Now, is 4 a factor of 68? Well, again, we can try to show using long division. And you can see here that when we divide by 4, when we divide 68 by 4, we get a remainder of 0. So 68 divided by 4 is 17 with no remainder, which proves that 4 is a factor of 68, as is 17. If 4 is a factor of 68, then 4 has to pair with another number to multiply together to equal 68. And it's 17. The other factor is 17. 4 times 17 equals 68. So we're just reviewing some simple concepts from arithmetic, early arithmetic, that are very important in understanding why we divide polynomials. Not just how we divide polynomials, but why we divide polynomials. what we're really getting at is when we divide a polynomial by another polynomial, what's the remainder? If the remainder is 0, then we have found a factor of the polynomial. And that's the most important concept in 3.4 and 3.5 is finding factors of polynomials. So this question right here, why is x minus 4 a factor of x squared minus x minus 12? Now we already looked at that up here. We know that x squared minus x minus 12 factors into x minus 4 times x plus 3. But the real answer to why is it a factor is because when we divide x squared minus x minus 12 by x minus 4, we get x plus 3 with no remainder. So that x minus 4 times x plus 3 is equal to x squared minus x minus 12. And what we need to learn then, or at least review for many of you, is how to show that division, or how to do that division. So we'll quickly just review the long division algorithm one more time with numbers, and then we'll look at it with polynomials. So we need to know how many times 14 goes into 45. And the answer is 3. 14 times 3 is 42. So now we multiply. The 3 times the 14 is 42. Draw the line and subtract. 42 from 45 is 3. Then we drop down the 6. 14 into 36 goes twice, because 2 times 14 is 28. Draw the line and subtract. 36 minus 28 is 8. So we have a remainder of 8. Now, a couple of vocabulary topics here, just not that these would be on an exam or anything, but I use these words in the course of the discussion, and you may read them in the textbook, so it's important to know what some of these words are. So the expression inside is called the dividend. What you're dividing by out here is called the divisor. The result of the division here is called the quotient. And then whatever's left over after dividing is called the remainder. So when we have 456 divided by 14, the result was 32. And I mean, depending on what level of mathematical understanding, when we learned division, early elementary, for example, we said, well, it was 32 with a remainder of 8. And then as you got a little more sophisticated in your mathematical understanding, you said, well, it's 32 plus the remainder over, oops, the remainder is now 14, plus the remainder, which is 8, over the divisor, which is 14. So 456 divided by 14 is equal to 32 plus 8 over 14. So when we have the dividend over the divisor, it's equal to the quotient plus the remainder over the divisor. And the way of writing this, if we wanted to use, well, we could say that the dividend is equal to the quotient multiplied by the divisor plus the remainder. Okay. So let's get in then and review how to do this long division algorithm with polynomials. We focus primarily on the first term here of the divisor and then this first term right here of the dividend. And we need to ask, how many times does x go into 6x squared? And the answer is 6x times. Or another way I like to think about it is, what kind of a term would I have to have up here so that when I multiply it by x, I get 6x squared? What we're trying to do is match this first term. So I've got to multiply x by something up here to match 6x squared. And so that term has to be 6x. And then what you do is you multiply the 6x by both the x and the negative 4. So 6x times x is 6x squared, and then 6x times negative 4 is negative 24x. Then you draw the line and subtract, just like we did with long division up here. You draw the line and subtract. That's why it's important that these two terms match exactly, because when you do this process, you want those first terms to cancel. And then minus a negative here, these both become plus, and so that's really negative 26 plus 24, which is negative 2x. Then we drop down the next term. Now, the question a lot of students ask is, when does this become the remainder, or when do you know that you have to keep going, or how do you know that you have to keep going? And the answer is, if this expression has a higher degree or the same degree as this expression, then you keep going. As soon as what you have here is a degree less than what you have here, then you can stop. Then this expression here becomes your remainder. So this is degree 1, that's degree 1. So this expression here is not a degree less at this point. So we need to keep going. We need to keep dividing. So now again we look at first term going into the first term. So how many times does x go into negative 2x? Or what can I put here so that when I multiply it by x, I match negative 2x? The answer is negative 2. Negative 2 times x now is negative 2x, and then negative 2 times negative 4 is positive 8. So now draw the line and subtract. This becomes, when you distribute here, this becomes a positive, so that cancels. When you distribute here, that becomes a negative. 12 minus 8 is 4. Now, this constant is considered to be degree 0. Any term that has no variable is considered degree 0. And this is degree 1. So the expression that we have left over here is a degree less than what we're dividing by, x minus 4, so this becomes the remainder. So our quotient is 6x minus 2. The remainder is 4. The book is going to ask you to represent this one of two different ways. One of the ways of representing the process we just did is 6x squared minus 26x plus 12 divided by x minus 4 is equal to our quotient, 6x minus 2 plus the remainder over the divisor. This is one way of representing our answer. The other way is to show just the dividend is equal to the quotient multiplied by the divisor plus the remainder. So it'll be clear in the directions which form they want you to represent as far as your answer. Okay, so another problem here for practice. One thing that's easy to forget but important not to overlook, the dividend, especially the expression that goes inside the long division sign cannot have any missing terms. What I mean by that is if we start with an x to the fourth, if this is a fourth degree polynomial, then we need to have an x to the third term, an x squared term, an x to the first term, and we have to have a constant. All of those terms have to be represented in the division, and we're missing x to the third. Here we have x to the fourth, we have x squared, we have x to the first power, and we have our constant, but we're missing the x to the third. So when we set up the long division, we have to have a 0x to the third, because 0 has no value, so 0x to the third also has no value, so we're not adding anything into the expression. This is acting as a placeholder to make the long division algorithm work, but it has to be there. And then we have 6x squared minus 3x plus 1. And then it's also true with the divisor. If the divisor is missing new terms, it's helpful to represent it with a 0 term, but it's absolutely necessary in the dividend. So 2x squared minus x plus 2. Okay, how many times does 2x squared go into 8x to the fourth? Because remember, we look at first term into first term, and the answer is 4x squared times 4x squared times 2x squared is 8x to the fourth. 4x squared times negative x is negative 4x cubed, and then 4x squared times 2 is 8x squared. Now we draw the line and subtract the whole expression. Remember to subtract the whole expression, not just that first term. So the first terms are going to cancel. This becomes a plus, so it's 4x cubed. This becomes minus, so this is negative 2x squared. And then we drop down and continue on. Now we're looking at 2x squared into 4x cubed. And that goes 2x times. So now it's just the 2x that we multiplied to that expression. So 2x times 2x squared is 4x cubed. 2x times negative x is negative 2x squared. And then 2x times 2 is 4x. So now we draw the line there, subtract. This term cancels. That becomes positive, so that term cancels. This becomes negative, so that's negative 7x. We still have this plus 1 here that needs to drop down. So plus 1. Now, this is degree 1. This is degree 2. So this expression here is 1 degree less than that expression, which means now we have our remainder. So we have our quotient here and the remainder there. So when 8x to the fourth plus 6x squared minus 3x plus 1 is divided by 2x squared minus x plus 2, then the answer is our quotient, 4x squared plus 2x plus the remainder over the divisor. That's one way of representing this. And remember, the other way would be dividend equals quotient multiplied by the divisor plus the remainder. So if we multiplied this together and then added those like terms, we would end up with that expression. And just kind of hinting into where we're going with this at the end of the lesson, and especially with 3.4, if there were no remainder, if the remainder were 0, then this process here of dividing polynomials gives us two factors with an expression that's otherwise not factorable. So if we had started with just 8x to the fourth minus 6x squared minus 3x plus 1, this doesn't factor using traditional factoring techniques. But if we can use long division, and if we get a remainder of 0, then we can find two factors of the polynomial. So that's where we're going with this. Now, we do have a remainder here, so since we have a remainder, that proves that none of these two expressions are factors of 8x to the fourth plus 6x squared minus 5x plus 1. Okay, so some of you probably remember from Math 1010, there's another way of dividing polynomials called synthetic division. But synthetic division only works if what you're dividing by, if your divisor is of the form x minus c. So it needs to be a first degree polynomial. It doesn't necessarily need to have a leading coefficient of 1. It is easier if it does. But most important thing is it has to be a first degree polynomial. And it doesn't have to be minus a number. It could be like x plus 2 as well, but it needs to be of the form x to the first plus or minus a number. So this is the example we started with here. 6x squared minus 26x plus 12 divided by x minus 4. So we already know what the answer is because we did it using long division. But we can show the same result using what's called synthetic division because the divisor is of the form x minus c. And so the synthetic division algorithm is slightly different. The long division bar is upside down, and it only uses number values. It uses no variables. And so the dividend that goes inside here in the top only uses the coefficients. So 6, negative 26, and 12. And then the divisor out here only uses a value, and it's the value that would make the divisor 0. So what value would make the divisor here 0? And the answer is positive 4. So when we synthetically divide, we're dividing by the 0 of the divisor. So once you've got it set up, the process is such. So this first number here always begins by dropping down to underneath right here. So I'm going to drop down the 6 all the way underneath. Any number underneath always multiplies with that number there. So I'm going to take the 6, multiply it by the 4, and then that result gets written right here, 24. And then any number that's written in a column like this adds. So negative 26 plus 24 is negative 2. So now the negative 2 multiplies with the 4, and that result, that product, is right here, negative 8. And since these are lined up in a column now, those are going to add to 4. The last number is always the remainder. Okay, these values here is your quotient. So 6x minus 2, and if you work your way backwards, this is a constant, and then the number next to it is an x to the first term, and if there was a number here, that would be an x squared term. If there was a number here, that would be an x to the third term. So you can work your way backwards there, and these are just coefficients of a quotient. So the result of the division is 6x minus 2, and then we have a remainder of 4, and then that's over the divisor x minus 4. So when 6x squared minus 26 plus 12 is divided by x minus 4, this is the result. Let's just check that against what we did here in the beginning. 6x minus 2 plus 4 over x minus 4, same result. Okay, now the same thing is true that if there are missing terms, especially in the dividend, they have to be represented with a 0. So we have x to the third, here we have an x squared, but there's no x term right here. And then we have our constant, which is 5. So we're missing that x term. And that's something that's easy to overlook, and it'll lead you to a wrong answer if you don't see it. So when we do synthetic division here, we take the coefficient 2, negative 7, but then we have to have a 0 where that x term would be. And then we have 5. And then the 0 of our denominator, or the term that would make the denominator equal 0, is positive 3. Now we go through the algorithm. This first number always drops down to underneath. So 2, and then 3 times 2 It's written here, so that would be 6. These values add, negative 7 plus 6 is negative 1. Now these terms multiply, and that's written here, which is negative 3. 0 plus negative 3 is negative 3. These terms add, or sorry, those terms multiply. Anything outside multiplies, so that's negative 9. These terms add to negative 4, so this is the remainder. This is your quotient, or at least the coefficients of the quotient. There's your constant, this is your x to the 1 term, this is your x squared term. So we have 2x squared minus x minus 3 plus our remainder over the divisor. Now, an extension, or application rather, of synthetic division involves using synthetic division to evaluate a polynomial. So this is something we practiced back in Chapter 2, evaluating a polynomial, the very first section, 2.1. So if we're given a polynomial here, for example, find p of negative 2, what we did in section 2.1 was simply, let's get the right color here. There we go. Plug in the negative 2. For all the x's. And then evaluated. Like this, and it takes a little bit of work to do by hand. Let's see, 50 times 16, that's going to be 80. And then let's see, negative 96 plus 80, negative 16 plus 32 minus 14 plus 3. So now we have 16 minus 14 plus 3. So that's 2 plus 3, which is 5. So that's what we would have done back in Chapter 2. There's something called the remainder theorem. The remainder theorem involves synthetic division. So if we used p of x as a dividend, so if we did synthetic division and p of x was our dividend, so that's the expression that would go inside. So we would have 3, 5, negative 4, and then there's got to be a 0 because there's no x squared term, and then a 7, and then a 3. And then if we divided by, so we're evaluating at negative 2, so the actual factor there is x plus 2. So we are still evaluating or dividing by negative 2. So we're going to do a negative 2 for the synthetic division here. And then if we just did the synthetic division algorithm, the remainder here would be p of negative 2. So let's just see if this works. Drop down to 3, and then multiply, then add there. Negative 2 times negative 1 is 2. And then add there. Negative 2 times negative 2 is 4. So then we add there. Negative 2 times 4 is negative 8. So then we add there. And then negative 2 times negative 1 is positive 2. So then we add there, and we get a remainder of 5. So p of negative 2 is equal to 5, just like we got here. So you can use this remainder theorem and synthetic division to evaluate a polynomial. It's a lot quicker, I think, to use synthetic division than to use brute force like we did here and evaluate a polynomial. At least, a polynomial with a higher degree like x to the 5th. So that's called evaluating a polynomial using synthetic division and the remainder theorem. Now what this has all been leading to is finding factors of polynomials. Synthetic division is a quick way to show that x minus c is a factor of p of x, because if we can show that when we divide p of x by x minus c and it's equal to a quotient with no remainder, then x minus c is a factor of p of x, as well as q of x is also a factor. So remember our discussion, if we find one factor, we've also found another factor. So we started with this problem in the very beginning, show that x minus 4 is a factor of x squared minus x minus 12. So the way to show that then is doing synthetic division. So if we do the synthetic division, we get a remainder of 0, and that's what we're going for, is a remainder of 0. A remainder of 0 means that this divides evenly with no remainder. And so this proves that x minus 4 is a factor. It also gives us another factor here of x plus 3 is equal to the original dividend. So that's how we show that an expression is a factor of another expression, is by dividing and hoping to get a remainder of 0. So show that x minus 1 is a factor of x cubed minus 7x plus 6, and find all other factors. Because what we're interested in is not just finding one factor, we want to find all three factors. X to the third minus 7x plus 6 is a third degree polynomial, meaning it has three factors. So we want to be able to find all of them. So show that x minus 1 is a factor, we do synthetic division, and it's missing an x squared term, so remember to put a 0 in there for the x squared term. And then we're synthetically dividing, so x minus 1, the 0 of that would be positive 1. And then we go through the algorithm. 1 times 1 is 1, then we add, and then 1 times 1 here is 1, and then we add. 1 times negative 6 is negative 6. We add and get a remainder of 0. So what we know now is x minus 1 is a factor, and this is the other factor right here. The quotient is also a factor, and this quotient is x squared plus x minus 6. And this is all equal to the original polynomial here. And so then it says to find all the other factors. We found this one. This is a factor, but we're interested in linear factors. We want all the factors to be of this form. And so what we need to do then is to continue to factor this quadratic expression into its linear factors of x plus 3 and x minus 2. So now we have all three linear factors of what we started with. And what we just did here is a pretty big deal, and this is going to be the main topic in section 3.4 and 3.5, is given a polynomial expression like this, can we find the linear factors of that polynomial expression? And the key, or the tool that we use to make this work, is synthetic division and finding remainders of 0. So that should do it here for lesson 3.3, dividing polynomials. Just as a quick recap, we started with practicing long division here, being able to divide using long division. And then we took a look at synthetic division. Remember, it only works if your divisor is of the form x minus c or x plus c. And then we used synthetic division here to evaluate a polynomial using the remainder theorem. And then using synthetic division, we were able to prove that one expression is a factor of another expression if we got a remainder of 0.